function is a state function. When you climb a hill, it doesn't really matter which path you go. You can go straight up 5-mile path, okay? And that's very steep. Or you can wind around and then going from the bottom of the hill to the top of the hill. The total elevation remains the same. So it doesn't really matter which path you choose. Eventually you get to the point where you have an absolute same elevation from where you were and when you were at the bottom here. So this is what the state function is all about. And in this case, when we say energy is a state function, so in a chemical reaction, when a chemical reaction happens, we don't really care if the reaction happens in one step or the reaction happens in multiple steps. Now, when we say that, when we use the word reaction, it could be a combination of chemical process and physical process. Example, when you burn hydrogen in the presence of oxygen, you get water. Now, we know water is a liquid. Now, eventually, when you look at the equation, the reaction there, hydrogen is a gas, oxygen is gas. When the reaction is finished, initially you generate a gas water vapor. Now, when you get the final product at room temperature is in the liquid form. So that is a chemical reaction between hydrogen gas and oxygen gas. Okay, and then once you have water vapor is condensing back into liquid. That's a physical process. Condensation is a physical process. So in this case, it's a combination. Now, how much energy do we generate from burning the hydrogen gas? Well, it's the total energy required. Say condensation is an exothermic reaction. Well, the breaking of the chemical bond between two oxygen atoms, breaking of the chemical bond between two hydrogen atoms, that requires energy. However, forming the chemical bond in water, H2O, releases much more energy than the energy required to break the chemical bond between hydrogen atoms and oxygen atoms. So the overall process, the overall process releases energy because the formation of water molecule in the gas form and the condensation of the gas water back into the liquid form, both processes releases energy. The total amount of energy being released is much greater than the total amount of energy required to break the chemical bond between oxygen bound and hydrogen bound. So the state function of energy there, we can figure out how much energy do we need to break all the chemical bonds. And we can also calculate how much energy will be released when the new chemical bonds are formed. And then we simply take the difference. So when you're doing the calculation about something that we call a state function, well, all you need to know is how much do we have at the beginning, how much do we have in the end. Take the difference. So it's a simple subtraction. So in thermodynamics, in the topics that study the energy aspect of chemical reaction and physical processes there, and there are 3 laws of thermodynamics there. And the first law of thermodynamics is the law of conservation of energy. Okay, so we say the topic of thermodynamics is actually an independent chapter in Chem 1 and 2. You will be actually spending more time and looking at the energy perspective of the chemical reaction here. So thermodynamics is the study of energy and its interconversion here. And we can always convert energy from one form to another, one type to another, okay? But the energy is always conserved. And so the first law of thermodynamics says the total amount of energy in the universe is a constant. Whatever energy we start with when this universe is created, well, we have a constant amount of energy. And you can convert energy from one form to the other, but the total amount is constant. Well, looking at the entire universe, that's a very large scope. We may not need to study everything that we have in the universe, and for the scope of chemistry there, if you are conducting a chemical reaction, you can single out a particular environment where you have your system, where you have your surrounding. As long as you study, and everything is happening within that system, well, you can just focus on a smaller scale instead of the entire universe there. So another saying of the first law of thermodynamics there is that perpetual motion machine is impossible. You cannot operate something that uses energy. You cannot have something to create energy without using some energy here. Now, throughout the history, and people are trying to come up with something that run without using energy, an instrument or machine that can work for us and do work for us without using energy there. Well, understanding of the first law of thermodynamics. So that's impossible. There's no free lunch. Okay, so you have to, in order to say generate electricity, you have to burn coal and you have to use hydraulic power and water dams and all that. You cannot create or convert in a way, and we don't like it. And as chemists there and physicists, we don't like the word creation, and because you're not really creating anything, you're just converting a particular amount of energy into another form. Okay, so, and that's something that we always want you to remember. Now, how do we quantify? The chemistry is quantitative science there. How do we quantify energy? Now, this is something that you probably saw on many of the labels of the food product there, and nutritional facts there. And you see the total amount of calorie there. Calorie is a measurement of the energy stored in food. How do we get these numbers? Well, since energy is a state function, it doesn't really matter how you convert the food into whatever product after the chemical reaction. You can burn it. When you eat it, while inside your body there, when you eat the food there, the food is being digested and then it's being converted into other things. In the meantime, energy is being released. Now, since energy is a state function, the total amount of energy in a fixed amount of food is going to be the same. It doesn't matter which way you consume it. You can burn it, you can consume it, and you can eat it, and then inside the body, and the biochemical reactions happens there. It's much milder. So the energy is being released slowly, and you can use that in your body, your cells and your organs, and your body can use that energy to support your everyday activity there. So these numbers were actually determined in the laboratory there. So how do we find how much energy we get from metabolizing a given amount of food there? Well, this is the process. We can use what we call a calorimeter. Okay, so you can measure out a certain amount of cereal and you put it in a bowl, and then you put electric wire in there, and you conduct electricity. You heat it up, you burn it. Now, when you burn the food there, the energy stored in the food will be released in the form of heat. And when that happens there, if you have water surrounding it, water is responsible for absorbing the energy being released. Okay. Now, the total energy being released from this fixed amount of food is the same. It doesn't matter if you burn it or you eat it. Okay. So we can do this in the laboratory there, and then before the reaction there, before you burn it, we can record the temperature of the water. Okay. After the food is completely burned, all the energy released. You have to have a fairly good insulation. So the amount of heat is only being transferred from the food into the water without getting into the outside of this chamber here. So we measure the temperature of the water again after the food is completely burned. Then the temperature change, thermal energy. So the amount of the amount of heat being released into the water, and based on the mass of the water, based on the mass of food there, we can figure out how much energy is present in a given amount of food. So that's where all those numbers come from. And this particular experiment is pretty much done on a daily basis in many quality assurance labs there in food plants there, because we need to make sure that we need to put that label, FDA requirement. So you have to put that label in there to give you the information. This is how it's done. Okay. It's just too time consuming to have someone eat that food and then measure the. It's impossible for us to quantify the amount of energy in that way in a biochemical reaction.